Surface irrigation. Surface irrigation is the oldest and most common method of applying water to croplands. Also referred to as flood irrigation, the essential feature of this irrigation system is that water is applied at a specific location and allowed to flow freely over the field surface and thereby apply and distribute the necessary water to refill the crop root zone. This can be contrasted to sprinkle or drip irrigation where water is distributed over the field in pressurized pipes and then applied through sprinklers or drippers to the surface. Surface irrigation has evolved into an extensive array of configurations, which can broadly be classified as 1. Basin irrigation, 2. Border irrigation, 3. Furrow irrigation, and 4. Wild flooding. Surface irrigation processes. There are three general phases in a surface irrigation event: 1. Advance, 2. Wetting or ponding, and 3. Recession. These are illustrated graphically in next figure. The advance phase occurs between when water is first introduced to the field and when it has advanced to the end. Between the time of advance completion, or simply advance time, and the time when water is shut off or cut off, is the period designated as the wetting or ponding phase. The wetting or ponding phase will not be present if the inflow is terminated before the advance phase is completed, a typical situation in borders and basins but a rarity in furrows. The wetting phase is accompanied by tailwater runoff from free draining systems or by ponding on blocked end systems. After the inflow is terminated, water recedes from the field by draining from the field and/or into the field via infiltration. This is the recession phase. All numerical models of surface irrigation attempt to simulate these processes. The basic phases of a surface irrigation event. Surface irrigation configurations. Choosing a particular surface irrigation system for the specific needs of the individual irrigator depends on the proper evaluation and consideration of the following factors: 1. Costs of the system and its appurtenances, 2. Field sizes and shapes, 3. Soil intake and water holding characteristics, 4. The quality and availability, timing of deliveries, amount and duration of delivery, of the water supply, 5. Climate, 6. Cropping patterns, 7. Historical practices and preferences, and 8. Accessibility to precision land leveling services. Maximum depth of runoff in surface irrigation. The maximum depth of runoff in surface irrigation is generally at the entrance or beginning of the course. It should not exceed the height of the ridge height, and it should not exceed 15 centimeters. The value of the ridge height can be calculated equal to the following two largest values. 1. The gross depth of irrigation, GDI. 2. Maximum flow depth plus 5 centimeters. Manning N. One of the most important considerations in surface irrigation evaluation and design is the changes that occurs on the field surface as it is irrigated. Newly tilled soil is usually hydraulically rougher than soil surfaces that have been smoothed by the flow of water during irrigation. On the other hand, surfaces such as borders and basins may become hydraulically rougher as crop density and size increase. Freshly constructed furrows typically have N values of about 0.03 to 0.05 depending on the soil aggregation. Previously irrigated furrows without crops growing in the furrow itself will have substantially lower N values. Measurements have been reported where these N values have been as low as 0.015. In the absence of more detailed information, it is probably sufficient to use an N value of 0.04 for first irrigations and 0.02 for later irrigations, but the user has an opportunity to apply judgment here where necessary. The Manning N values for borders and basins vary over a much wider range than they do for furrows, primarily because they are affected by the crop and the geometry of its crown. A freshly tilled and prepared border or basin with a bare soil surface probably has an N value about the same as for furrows, 0.03 to 0.05. After initial irrigations and before substantial crop growth, the N value may be as low as 0.15 to 0.02, but later as the water is impeded by the crop, the N values can be as high as 0.80 for a crop like an alfalfa grass mix. Table: recommended design values for the Manning's roughness coefficient in the basin and border strip irrigation. Several methods have been presented for estimating Manning's roughness coefficient for furrow irrigation, as follow. 1. Trout, 1992, performed several experiments on 6 m long furrows with the assumption of flow rate uniformity, and presented the following empirical equations in power and exponential forms. Equations 1 and 2, for estimation of Manning roughness. N equals 0.0086 v 0.65, 1. N equals 0.048 e, 5.85 v, plus 0.01, 2. Where v equals flow velocity, m/s. N equals Manning's roughness coefficient. 2. Sepaska and Bonder, 2002, suggested that equations 3 and 4 be used for estimating Manning's roughness coefficient before and equation 5 after germination in furrows as follows. N equals 0.1162, 0.05037 q, 3. N equals 0.145 to 0.0142, and 0.0504 q, 4. N equals 0.0903 plus 0.0007991 c, 0.04 q, 5. Where N0 equals number of irrigations. Q equals inflow rate, L/S. C equals the percentage of vegetation cover. Basin irrigation. Basin irrigation is distinguished by a completely level field with perimeter dikes to control and/or prevent runoff. Basin length. Length of run in excess of a 400 m seldom is satisfactory. Basin geometry. In the absence of field slope to aid the movement of water on the field surface, the run length, or distance the water has to advance over the field tends to be minimized. Many basins take on a square rather than a rectangular shape, but this depends entirely on the availability of sufficient flow rates and the intake characteristics of the soil. Border irrigation. Border irrigation looks like basin irrigation and operates like furrow irrigation. Fields may have a slope along the traditionally long rectangular fields but cannot have a cross slope. The flow covers the entire surface and may be blocked at the downstream end to prevent runoff. Borders can also follow the contour lines in terraced fields. Border geometry. Borders are usually long and rectangular in shape. Often referred to as border strips, borders contain the flow within side dikes to direct the flow over the field. Borders can be furrowed where necessary for elevating a seed bed or compensating for microtopography within the border. Borders can also be level or nearly level, making them effectively the same as basins. Distinguishing borders from basins is often based on the rectangular shape rather than slope, and in any event, the differences are only semantic. Border strip length. Long border strips are easier to farm than short strips because fewer turns by farm equipment are required. Some of the factors that can determine the maximum length of run in specific fields are flow hydraulics, field boundaries, and barriers such as stream channels and drainage ditches, and changes in soil and inland slope. Border strips should not be laid out across two or more soil types that have different intake characteristics or different available water holding capacities, or both. Also, border strips should not extend across slopes that differ greatly from each other in steepness and length. Occasionally, slope, soil, and hydraulic conditions are such that an extremely long run seems feasible. However, the time required to patrol long runs and the difficulties in determining and making needed adjustments in stream size usually make these runs impractical. Length of run in excess of a 400 m seldom is satisfactory. Border strip width. Maximum width is influenced largely by the difficulties in keeping water spread over the entire width of a strip. Under normal construction, wide border strips are expected to have greater differences in cross-slope elevation than narrower strips. As flow depth decreases because of increased slope, minor surface irregularities in the border strip may cause incomplete water coverage. For this reason, the border strip width must be reduced as irrigation grade increases, as in the next table. Table, recommended maximum border strip width. Furrow irrigation. Furrow irrigation is at the opposite extreme of the array of surface irrigation configurations from basins. Rather than flooding the entire field, small channels called furrows and sometimes creases, rills. The amount of water per unit width on a furrow irrigated field may only be 20% of the water flowing over a similar width in a basin. Infiltration is two-dimensional through the wetted perimeter rather than a vertical one-dimensional intake. Furrows can be blocked at the end to prevent runoff, but this is not a common practice unless they are used in basins or borders to compensate for topographical variation or provide a raised seed bed to minimize crusting problems. The distinction between a furrowed basin or a furrowed border and furrow irrigation lies in the semantic preference of the user. For purposes of evaluation and design, both of these situations would fall under the term furrow irrigation. Field geometry. Furrow irrigated fields generally have slopes in both the direction of the flow and the lateral direction. These slopes can vary within a field, although the slope in the direction of flow should not vary significantly unless it is flattened at the end of the field to improve uniformity. One of the major advantages of furrow irrigation is that undulations in topography have less impact on efficiency and uniformity than they do in either basin or border irrigation. Corrugation spacing. The spacing of corrugations also depends on how rapidly water moves laterally through the soil. Because they are generally independent of crop spacing, corrugations can be spaced readily according to the soil intake characteristics, the depth of irrigation desired, and the corrugation grade to be used. They generally can be farther apart on fine textured soils than on coarse textured soils and closer on steep slopes than on flat slopes. The next table can be used in selecting corrugation spacings. Table, maximum corrugation spacing, cm. If the corrugation grade is 2% or less, spacing can be increased to the next wider spacing, such as from 38 to 45 or from 55 to 60 centimeters. Furrow length and maximum stream size. The practical values of maximum furrow lengths, m, depending on slope, soil type, stream size, and net irrigation depth, as shown in the next table. Table, practical values of maximum furrow lengths, m, depending on slope, soil type, stream size, and net irrigation depth. Summary of surface irrigation methods. Choosing one type of surface irrigation over another is very subjective because of the number of criteria to consider and the complicated interactions among the criteria. Table below gives a general summary of the discussion above and some typical comparisons. Table, a general comparison of surface irrigation methods. Surface NRCS Surface Irrigation Simulation, Evaluation, and Design Software. 2 generations ago, engineers relied on tables, nomographs, and slide rules to choose a flow and a field length. Rules of thumb led to choices of flow, length of run, and slope. A generation ago, the slide rule was replaced by programmable handheld calculators and computer models supplemented available tables and nomographs. Calculation of advance and recession trajectories allowed the irrigation specialist to more accurately evaluate uniformity and efficiency. Realistic assessments of the impact of changing flows, length, and slopes were possible. Today, the personal computer has replaced all of its predecessors. Information is online and real-time. Rules of thumb are almost entirely unknown in current curricula, and very few graduating engineers have even seen a slide rule. Analyses now focus on hydrodynamic, zero inertia, or kinematic wave models. Tomorrow, most of what is carried in a briefcase will be carried in a shirt pocket. And perhaps, a new generation of biosensors will be available that will allow surface irrigation systems to be managed online and real-time. In recognizing the need to update designing surface irrigation, the NRCS also recognized the need to provide modern tools for simulating, evaluating, and designing surface irrigation systems. The NRCS Surface program was written to fulfill this need. Surface is a comprehensive software package for simulating the hydraulics of surface irrigation systems at the field level, selecting a combination of sizing and operational parameters that maximize performance, and a convenient way to merge field data with the simulation and design components. The programming uses a 32-bit C++ language to encapsulate the numerical procedures, which describe the hydrodynamic theory in general use today. The software has been written for IBM-compatible micro or personal computer systems utilizing Microsoft Corporation's Windows 95 or later operating systems.